Okay, so can you can see my screen, right, all of you? Hello? Okay, yes, yes, blank screen. Okay, so let's start the class for today. Uh, till last day, we actually have completed the analysis of many algorithms for sorting. Today, we will recap what we have done and we will go forward. So, basically, the data structure that we are uh, learning over here, you see, if you divide the data structure in two parts, in one side we have, just a minute, just a minute. Linear data structure, and on the other side we have non-linear data structure. So what is this linear data structure? You can say that in case of linear data structure, data has data are organized in sequential form manner. If you try to run the, if you try to act, I mean, visit the all the node, all the value, then you can visit it by only one run. I mean, so the data can be all the data actually, all the data can be visited in a single run. What is an example we have seen over here? Till now, all the data structure that we actually have discussed are linear data structure. For example, if we start from array, even array is also a data structure, right? Array, stack, queue, linked list, all type of linked list. These all are example of this linear data structure. Now, if we go for non-linear data structure, obviously the data has are not organized in sequential manner. Actually, you can say that data are organized, sorry, in some hierarchical manner. So that's why if you try to visit the data, you cannot visit all the data in a single run. So all the data cannot be visited by single run. Now what does single run mean? I'm trying to say is that if you have, say for example, linked list over here, so if you have a number of nodes, something like this, and if you want to traverse all the node, you start journey from here and you have a path, right? So by a single run you can go from first to last. But it's not something like happen over here. The reason is that we will realize the reason very soon. But before that, just for time being, you remember this one, that it cannot be visited by single run. And what is an example of this? Example of this is, for example, tree, graph, and many more. Okay. So we will start with tree form today. Uh, and let's go for that, what tree is. So we will start with intro. I'm sorry. So now let's define what is tree first. You can say that actually the definition is a recursive definition. A tree T can be defined recursively as a collection of nodes having parent, child relationship. So what does it mean? Let's first draw a tree, example tree for you, so that you can realize it. So suppose you have three data over here, right? You have three data A, B, and C, and these three data you want to store in linked list. In that case, what you will do? You will just create a node, and we'll do something like this, right? It's easy for you. You have done this. Now, in case of tree, it will be something like, you can draw the tree something like in this way. So this is an example diagram of a tree where this A, B, C is having some hierarchical relationship, and where A is basically parent of B and C. Now, maybe the data, a lot of more data can be present. I mean, maybe I have a data something like this. Some more data, say C, D, E, F, G, and many more in this downward. So this, in terms of practical example, this is what you will find this structure when you will join in some IT company. Not in IT company, actually in any company. So when you will join, maybe you will have some post, something like graduate engineer training or something like that. And actually, you will be in this particular level, in this particular part. So this is, for example, consider that this is the chairman, and under this chairman having some managers, and under the managers we have all the engineers. So your entry will be from here, and maybe because of the promotion you can go upward. Okay. So now we will, before we go many details about the work, I mean, of the tree, we have to understand some terminologies about this tree. So for example, the first one is root. What is root? Root of a tree. This is actually what we call root. This one, what we call root. Why it is called root? If you just invert this particular part, I mean your structure is something like a fashion, something like this, right? So if you invert this one, it will become like this. And we have a tree. If we have a tree, we have a lot of we have root over here, and we have a lot of branches from this side, right? So something like this fashion having we are getting. So where the root was present, root is present somewhere here, but we are checking in this way. So that means this is what root is. That's why the first one we call root. Now how you can define a root? We can say that it is a node which does not have any parent. Okay. Similarly, next terminology will come leaf. What is leaf node? Leaf node is this one, You are actually leaf node of your company when you will join. Just something like it's a leaf is present somewhere over here, right? In all these places. So leaf is at the last level. What you can see is what you call leaf node. So by definition, you can say a leaf node are the nodes which does not have any child. Those are called leaf nodes. And obviously, other nodes like those are present over here, these are called non-leaf nodes. Obviously, you can say that root is also a non-leaf node, right? So this non-leaf node, I mean, you can say that root belongs to non-leaf node. Okay. Now, next one will come is what we call sibling. Just a minute. Okay. How you can define sibling? You can say that the children having same parent. So normally these words we use frequently in our daily life, and actually the word has the same meaning in case of a data structure subject also. So you can say that here this B and C are sibling, D and E are sibling, but not E and F. F and G are siblings, right? So now Next one will come is degree of a node. This is defined. It is defined by the number of children of a node. Now here we have a node. In a tree, the number of children can ranges from 0 to plus infinity. There is no restriction. You cannot say that you cannot have a, there is no, it's not possible to have a tree with 5 children or 10 children or 5 lakh children. Okay. So it can be anything. Now obviously depends on the number of children. We segregate the tree in different way. That's another issue. But there is no restriction about the number of children theoretically in a tree. The next question will come that then what is degree of a tree? That was degree of a node and now it's degree of a tree. Obviously, it's not guaranteed that each and every node will have equal amount of children. Some node may have 1 children, some node may have 2 children, some node may have 3 children. So a tree can be something like this also. I mean, we have some node over here, then this side, and then we have 1 children, and here we have 3 children, and then here we have 2 children, and then here we have 3 children again, and here we have 4 children. So anything is possible. This is a valid tree. And I think you can understand each and every terminology with respect to this tree also. So for example, degree of a this one. What is degree of this node? Degree of this node will be 2 because it has 2 children. Degree of this node is 1 because it has only 1 children. Degree of the leaf node is always 0 because leaf node doesn't contain any children. Now comes what is degree of tree. Degree of a tree can be defined the maximum degree of a children of a node actually of the tree. So for example, in this situation, this particular node contain 4 children. No other node contain 4 children, right? So degree of this is 4. Right. Now, just a minute. Now come to the next definition, that is depth. level of a tree. What is this? Let me write it first. It is length of path from root to that node. So you can easily say that if I ask what is the depth of this particular node, it is the length of the path from the root to that node. So if you start journey from here, do not consider start from O1. So it's O1, 1, 2, 3, and then 4. So depth of this node is equal to 4. This is also called level. So you can define in this way, also pictorially show in this way that this is in one level, this is in next level, these are in. So this is level 0. Because if you start journey from root, so root to root doesn't require any path. So the length is 0. It's equal to 1, it's equal to 2. These all nodes are in level 3. These all nodes are in level 4. These all nodes are in level 5. And this is in level 6. So the next point have come. What is height of it? Height of a node, sorry, not height of a tree. You can say that number of edges in the longest path from that node to a leaf node. You see, I'm not specifying any leaf node. This is important. Why? For example, if you take a tree something like this, so take a simple tree, something like this. Okay, so if someone asks you that what is the height of this particular node, it's given that number of edges in the longest path from there. So if you forget about the longest word, if you think that number of edges of the path from that node of a leaf node, so from this node you can reach multiple leaf nodes. You can reach this leaf node, you can reach this leaf node, you can reach this leaf node. So which path I will take? Obviously it's a confusion, and that's why it is considered longest path. Because if you start journey from here, this node will take only 1. This node will take 1, then 2. And this node equal 1, then 2, then 3. So that means height of the node will be equal to 3. So before I proceed, do you have any question? Any question regarding what we have discussed till now? Anybody has any doubt or question? Okay. Now, as I have told you that the number of children can be anything in a tree. So depends on that, you can define tree in different way. You can you can actually, we can have different type of trees. Some trees are called binary tree. Some trees are called ternary tree. Ternary tree means three children. Binary tree means two children. So in our syllabus, or we will specially concentrate on this binary tree. And many other variations of tree also present. So one by one we will go for some and more advanced tree after completion of the initial concept of the binary trees. So now what is binary tree? It is a tree, sorry, having all the non-leaf nodes sorry, not having, I should write which, where, sorry, where all the non-leaf nodes have maximum two children. What does it mean? It means that this is a binary tree. It's a binary tree. This is also a binary tree. It is also a binary tree. It is also a binary tree because each and every non-leaf node contain either 0 or 1 or 2 children. I'm sorry, 0 children is not possible. Because if there is 0 children, it becomes leaf node. Something like this. All these nodes are leaf nodes, right? Because it contains no children. That's why it is given all the non-leaf nodes have maximum 2 children, not more than that. So somehow by any chance if you find that you have a situation like this, it is no more a binary tree. So in this way, that means we can have lot of different type of variation in binary tree, and depends on that actually binary tree has been categorized in many ways. So we will mainly discuss three of them over here initially, and we will go for some advanced category later. The first one that we will see is what we call full binary tree. What is full binary tree? It's very easy. The criteria is that each and every node has either 0 or two children. It means, I'm sorry, it should be each and every non-leaf node. No, non-leaf node is not there because either 0 or 2. So presence of 1 is not there. I mean, you can say that this is a full binary tree because it has 0 children. But you cannot say that this is a full binary tree because this particular node contains 0 children, fine, but this node contains one children which is not accepted. It should be either 0 or 2. So it becomes full binary tree. But if you add this one, it will not remain a full binary tree. If you again add this one, then also it will not it will not be a full binary tree. To make it full, you have to connect them all. Either children will be both or nothing. So it can be a full binary tree. Something like this. Second one, we will discuss what we call complete binary tree. Here you can say that all the levels are completely filled except possibly the last level. This is point number 1, and another point number 2 is that nodes in the last level are filled from left to right. What does it mean? Let's take an example. So you can say that suppose you start from here, so this is a root node. Obviously, with only one node, this particular criteria is not properly visualized. So let's draw two more children of this node. It is a binary tree, and you can say it is a complete binary tree also. This is also a full binary tree, and also it is a complete binary tree, but still it is not visualized properly. What it is saying that all the levels are completely filled except possibly the last level. So this is level 1, this is obviously level 2, I'm sorry, this is level 0, this is level 1. Just a minute. Somadip, Somadip Kormokar, why you are so late? Did you got message yesterday? You got, right? Okay. Anyway, so here level is 1. If you keep on adding many more nodes over here, it is saying that all the levels are completely filled up except possibly the last level. So that means if we have many other nodes under these two nodes as a children, then that level of that nodes will become the last level. So, for example, if you draw this one, only one node over here. Obviously, I can add many other nodes, but I can say that here I have at least that node, so it is level 2. So this is the last level till now, and it is given that all the levels are completely filled. Levels are completely filled means in that level, the number of nodes that I should have all are present. That's what it's saying. So that means this is the last level. Other than this last level, all the levels, that is level 0 and level 1, is completely filled. Second point is that nodes in the last level are filled from left to right. That means first the furthest left, and at the end it will be filled with farthest right. That means as I have added this one, next time if I add this one over here, this tree will no more remain a complete binary tree, because obviously all the levels are completely filled except the possibly last level. So this first criteria is fulfilled with this tree, but the next criteria is not fulfilled. That is, nodes in the last level are filled from left to right. You have filled left one, fine, but before filling right one, you have filled this one. That means to make this tree as a complete binary tree, I have to add this tree node over here also. Now it become a complete binary tree. Now assume that I want to add many other nodes, and suppose you start considering that you are following this second point. Nodes in the last level are completely filled from left to right. So if you go for the next level, level 3, so obviously you will add from the left, but still this tree will not remain a complete binary tree, because now it is violating point number 1. What it is saying, that all the levels are completely filled except possibly the last level. Obviously last level is not filled up, and I am not bothered about that, but all the levels are not completely filled. Level 0 is completely filled, level 1 is completely filled, but not level 2. There is one more space to store one more node of this particular, one more child of this node. Now to make this tree as a complete binary tree, at least there is no, if you still add nodes over here, then also it is not complete binary tree. To make it is complete, you have to add this node, fill up this particular level. So now we will go for third point. That is perfect binary tree. How you can say that all the internal nodes have two children, and all the leaves are at the same level. Now question is that what is internal node? I forgot to define this. this term actually. So let's define it first. What is internal node? All the nodes except root and leaf nodes are called internal node. So if I just define a tree, this one is root. It can be internal, it can be internal. If I say this is internal, it must have some children. And if I say it is a leaf node, it means it cannot have any other, children. If I have some children over here, then this L will become internal node. And since it is internal, it may not have any children, there is no issue. I'm not specifying any particular tree. I'm saying for any tree, these are internal nodes, which are not the nodes except leaf node and the root node. So what is an example of perfect binary tree? I hope you can understand that if we want to keep this criteria, a perfect binary tree should always look something like this. Because all the internal nodes having two children. So only one children is not even possible. And all the nodes are at the same level. All the leaf nodes are in the same level. Obviously, all the leaf nodes are in the same level. So from these three different type of binary tree, if we want to make relation in between them, you see, this perfect binary tree is a complete binary tree also, right? Because all the levels, possibly the last level is filled up. It is not saying that the last level will never fill up. It is saying that possibly the last level. It means that if the last level is not filled up, then also I can say a tree as a complete binary tree if two criteria is hold. One is the other levels are completely filled up, and second is that in the last level data are filled up from left to right. But if I find a tree where the last level is also filled up, then also it is okay. It can be a complete binary tree also, right? So that means every perfect binary tree, we can say that every perfect binary tree is also a complete binary tree but reverse is not true. So this is an observation. We have seen, right? And even you can say every perfect binary tree is also a full binary tree. So every perfect binary tree is also a full binary tree because it contains either 0 or 2 children. But reverse is not true. But you see, you cannot make relation between full binary tree and complete binary tree. Because if you don't have this node, if I don't have this node, then also it is complete binary tree. But it is not full binary tree. And if it is a full binary tree, then since the last level is not filled up from the left to right, there is no rule over there. That's why a full binary tree cannot be a complete binary tree. So if you make a Venn diagram with these three set, this Venn diagram will look something like the set of its perfect binary tree. I'm sorry, I had a mistake. We need a separate diagram. I mean, if this is a perfect binary tree, in the above, if this is perfect binary tree, then it can be complete. Or it can be, if it is a perfect binary tree, then it can be full binary tree. But you cannot make any comparison between full and complete. Another thing we have that is binary search tree. What is binary search tree? It is a binary tree. Any type of binary tree. There is no, it's not, it can be perfect, can be full, can be complete, doesn't matter. Where we have a constraint, that is left child is less than parent and parent is less than right child. The value, some value, that can be age, that can be anything, that depends upon the problem type. So what is left child? Obviously, if this is a parent, the child in this one is called left child, and this side we have right child. By the way, one thing I forgot to tell you, that the tree that I am drawing, for example, say B, C, D, E, F, maybe G, like this. Suppose this is that tree, some binary tree. And if I consider binary search tree, doesn't matter, whatever. One thing I had a mistake, that we are connecting this A and B. But question is that we have not yet considered any direction. I mean, if you start journey from here, obviously you can go either B or to C. So, but if you standing on B, there is no way to come back to A. It's something like a single linked list between A and B. So always remember direction is actually you can say top to bottom. This is direction. Something like this. And obviously the total whole data structure will be uh, defined will be in a dynamical fashion. So naturally the similar type of concept we have to use as we have done in linked list. So how we will do that, that's latter issue. But one thing is sure that there is a way from jumping B to G, but there is no way to go directly from B to A. So if you want to go back, you have to use some intelligent algorithm. And if I assume that this is a binary search tree it is representing, so obviously you can say that B must be less than A and C must be greater than A. So a possible binary search tree with values will be something like 10. In this side we have 5, we have 15, here we have 12, here we have 20, maybe 18, maybe 7, 6, 2. Now see, one thing very interesting point is there is that we're saying that left child is lesser than parent and right child. Actually, you should say that left subtree is less than parent, parent is lesser than right subtree. Now what is right subtree? This is what you can say subtree. So if you cut this part, it is also a binary search tree. So that's why this part with respect to the whole tree is called subtree. And if you check all the values are lesser than 10. Similarly, you have a subtree over here also. And in the right subtree, you see all the values are greater than 10. So the relation is actually recursive. With respect to each and every node, as a parent, it is true. For example, if you take 5 as node, the left subtree of 5 is this one, and right subtree of 5 is only this one. And if you compare, the left subtree lesser than its parent, and parent is lesser than its right subtree. Similar thing applied over here also. So this is an example of binary search tree. Simply we call PST. Any question you have regarding what we have discussed till now? Anybody? Yes. Yes, yes. This is what I'm saying. You, how it is possible you can put 20? First of all, you have to have some lesser value. I mean, you must have some value lesser than 7 in the this side. Right? If you put some lesser value, Instead of 7, if you put 20, then this 20 is greater than 10. So T20 cannot be in the left side of 10, right? So when we will design this binary search tree by algorithm, the algorithm you will see that the algorithm is designed in such a way that it is not possible to put any maximum value which is greater than a node in its left side. It is not possible. The algorithm will not do that. I mean, algorithm actually will restrict you to do that. Okay. Okay. Any other question? Any other question? Any other question? Okay. So we can stop over here for today with all these definitions and basic concepts. We will go for this binary search tree in detail from the next week. Thank you. Bye.